Hello, everyone, and welcome to the latest edition of our podcast and lightning interview series. So as you know, we always want to make these sessions interesting and interactive. So please do introduce yourself on our chat channel. You should see that to the right or underneath your screen, and tell us where you're joining from and what you do. And of course, please feel free to add your questions to this conversation. So as you know, we are interviewing the renowned Professor Allen Downey today. But first, before I get to that, I want to share a few quick slides. Lots of interesting events coming up at ODSC. Next week, we have an interview with another fantastic ODSC speaker, Michelle Yee, who spoke at ODSC West last year on generative AI. So we've got some interesting topics we're going to discuss with her. And a couple of other things I wanted to highlight is, of course, ODSC East 2024 is back in person in Boston, April 23rd to 25th. So we're hoping you can join us either in person or perhaps virtually if you can't make it to the beautiful city of Boston. And another quick thing I'm very passionate about is you may have heard Andrew Ning was July of 22 or 23, hard to keep track. But he was advocating for data-centric AI. And I think even before that, a lot of us came to AI and data science via data engineering in particular. So we're excited to co-locate our second data engineering summit. That'll be our second annual data engineering summit. So we've got 2 days of data engineering, lots of very talented and accomplished speakers from the data engineering world. So I think that'd be of interest to you as well if you wanted a bit of data engineering sprinkled in with your AI and data science. And we'll have some of those sessions available virtually as well. And as you may or may not know, we're also turning these live interview sessions into our podcast. We call our AIX podcast, X standing for whatever topic we're discussing on the day. So if you have a chance, please go out there, check out a lot of our great past interviews. We have about 30 or so sessions at this point. So please go check those out and subscribe if you're on Spotify or Apple, whatever. So on with the show for today. So you may know Allen Downey from ODSC, but more likely not, you know him from the fact that he's a renowned educator, author, and data scientist. He's a professor emeritus at Olin College and also a curriculum designer at Brilliant. He's particularly famous for his accessible and influential textbooks such as Think Python, Think Bayes, Think Stats, and I'm leaving out half of them right there. But if you haven't seen these books, I would suggest that they're very well worth the read. And Allen's commitment to education is also underscored by his open education philosophy, and thus many of his books are published under free licenses, making them accessible to students, educators, and everyone else worldwide. He's a particularly active blogger, mostly focusing on Bayesian statistics, a field which we know from ODSC he's particularly passionate about, and his blog, Probably Overthinking It, reflects his expertise and enthusiasm for making the complex statistical concepts accessible to a broader audience. And his latest book, and the topic for today's discussion, is also titled Probably Overthinking It. Allen, welcome to the show.
Thank you. Thanks. It's great to be here.
So Allen, I think you came to the first ODSC East back in April, 9 years ago. So ODSC, you're well known to that audience, and I just give a brief bio, but give us a little bit more background around yourself, about yourself, and what you're up to currently, and then we'll get into the topic of today.
Right. Well, I mean, you said it. I'm a recovering academic. I was on the faculty at Olin College for almost 20 years.
Oh, wow.
I left just a couple of years ago to just explore and start to work on whatever comes next, and still kind of figuring that out. But I've been writing lessons now for Brilliant and online lessons in programming and data science. So that's always what I'm interested in, and exploring and seeing what comes next.
That's great. So you're on an extended sabbatical, as they say in the academic world. And I've been checking out some of your lessons in Brilliant for the last 9 months or so, and what you guys are doing there. So great site. I would encourage people to check out Alan's work there as well. But as I mentioned in your bio introduction, you're the author of many books. Think Stats, Think Bayes were two of my favorites. Even Think Python. When I first got into Python, I was reviewing that book, but why another one? So what's the inspiration behind this?
Yeah, this is a different project for me, because those books use a lot of Python code to explain technical topics. And this is for a general audience. This is my first attempt at popular nonfiction. Although I will say it's an audience that needs to be comfortable with data. It's a challenging book. I've heard from people that they appreciate that I'm explaining things clearly, and I'm glad to hear that. But then they usually follow it up by saying, "But it's pretty hard." So I think both of those things are true, but I think it's worth it. It is a collection of topics that came from the blog originally. And that was my first thought, is that this was going to be like the best of, and it was just going to be a compilation. But it ended up evolving a bit into what I think is an optimistic take on data. And this is the idea that we really can answer questions. We can make better decisions when they're guided by data. And maybe we can even settle arguments. Maybe people will come to agree if we can line up the evidence, but it's not always easy. And that was the other thing that kind of bubbled up in the book, is all of the statistical paradoxes, all the ways that data can fool you. And so that became the organizing principle of the book, is what are the ways that it can go wrong, that we can get fooled, but what's the benefit if we get it right? Better decisions, answering questions.
So I guess it's that old adage, lies, damn lies and statistics, right? But I love the way you wove data, statistics, and stories into your book, and we're going to get into that. But one of the topics we had for today's conversation was the statistical traps that sometimes people fall into, or fallacies. Definitely data traps from data engineering, data transformations. We see that all the time. So we'll delve into some of these in details. But what are some of the most, because you just said it, you were inspired to write this book, you've seen that, but what are some of the most common statistical traps or data traps or logical traps you see people occurring in day to day? And again, I encourage people, we're going to share a link to this book because there was so many great examples in the books, but just highlight maybe some of your favorites, because we're going to dive deeper into in a bit.
Right. Well, I mean, the biggest one, the thing that comes up over and over in the book, is different forms of non-representative sampling, where you've got something going on in your sample that is not what's going on in the world. And there are many ways that can happen. So there are different phenomena from different kinds of biased sampling. But that's the big one, the one that comes up over and over. And that can be, like a formal sample, like you've done a survey or you're doing science, and these things can come up. But it also happens in real life, just in walking around and reading the paper and observing the world. You're not seeing a representative sample. You're always seeing things that have gone through a selection process. And that process changes your perception of the world in predictable, consistent ways.
Yeah, no, absolutely. And you delve into that in your book in a couple of different places. I think one was the inspector paradox, and then lent bias sampling. But before we get in there, I want to kind of start with the first chapter of your book, which I really love the way you phrased this. Is and you had a blog about it as well, and so people can go check out the blog. But like you said, at least in a mathematical sense, no one is normal, everyone is weird, and everyone is the same amount of weird. And I thought it was a very clever play on words, and Can you describe what you meant by that and describe what that chapter is dealing with?
Sure. Yeah, right. Nobody is normal. Everyone is weird. And we're all the same amount of weird.
Right. And nobody take offense by that.
Yeah. All right. There are two parts of that. And the first one, let's say that you just look at one measurement like height. We have an intuition for that. We understand that most people are close to average, and people who are much, much taller or much shorter, that is relatively rare. So in one dimension, that's how it works. We kind of understand that. When you start looking at more and more measurements, though, what you find is that nobody is close to average in every way. So if you take 10 measurements, you will find that almost everybody is average on some measurements, but outside of the average on at least one, maybe two, and so on. And so that's well known. There's a famous study from the Air Force from the 1950s where they did exactly that. They were trying to design an airplane cockpit. There were 10 measurements that they needed to fit. And what they found is that out of 1,000 pilots, there was nobody who fit the cockpit on all 10 measurements. Everybody was far from average on at least one. So that was the conclusion, is that you have to customize things. If you need to fit 10 different measurements, you're going to need to customize. That's familiar. And then in this chapter, I took it a little bit farther, because if you look at not just 10 measurements, but all the different ways that people vary, all of the physical measurements, all of the psychological ways that people are different, and you add up all the weirdness. So in the book, what I did is I gave everybody 1 point for every measurement where you are far from average. And the far from average meant, I think, more than about 1 standard deviation from the mean. So you get a weirdness point on every measurement where you are 1 standard deviation from the mean. And if you add them all up, what you find is that the distribution of points is a relatively narrow distribution. We all have roughly the same number of weirdness points, which means that in this multidimensional space, we're all roughly the same distance from the origin, the same distance from average. And so in that mathematical sense, we are all equally weird.
That's interesting. So, because you also illustrate in your book how best to model that in a statistical sense. So linear relationships versus log normal distributions. Can you explain that a little bit to our audience and give them some insight into how best to, when you're dealing with those kind of distributions, how to model them?
Sure, yeah. And this is one of the themes of the book, is not everything is a Gaussian bell curve normal distribution. Things like physical measurements often are. And so if that's your model for, height and, arm length and things like that, it works really well, except for one measurement in the data set that I looked at. The one exception was weight. The distribution of weight does not follow a Gaussian. If you take the log transform, if you take the logarithms of the weights and you look at that distribution, it is roughly Gaussian. So if the logarithms are Gaussian, that means that the values themselves follow a log normal distribution. And at first you might think, well, so what? But they really are there qualitatively different in the way the tail of that distribution looks. One way to think about it in terms of height and weight, the tallest person in the world ever, and I forget his exact height, but he was about 60% taller than average. So the tallest person ever wasn't even twice the average height. But the heaviest person ever, reliably measured, was 8 times the average weight. And that's, again, because the weights follow this log normal distribution, the tail goes much farther out to the right. And the behavior there is different from what we expect. If you're expecting Gaussian behavior, you'll be surprised by weights, but you'll also be surprised by things like running speed. That fast runners are much faster than you think, and they're much faster than average.
Yeah, because I think it was one of your presentations, or was it your blog? But living in Boston and being Irish, I follow the Red Sox only when they're winning, so I'm definitely a fair weather fan. But was it? Yeah. So in baseball, so apologies for those who know this, and I'll explain if you don't. But you had this example which was fascinating. So there's in baseball, there's this mascot called the Freeze, which is an interesting name considering what he does. So during the breaks in baseball, and there's a lot of breaks in baseball, he's racing a fan, which doesn't sound like much, but he's dressed in this kind of crazy turquoise suit, and the fan gets a 5 or 6 second head start. And that doesn't sound like much, but trust me, like these fans are pretty fast, and 5 or 6 seconds over maybe, I don't know, it's a 100-yard dash. I have no idea how the length of it is. You see the fan take off, then you see the Freeze take off, and just to watch that video, and I know it was one of your blogs, so I'd encourage people to go to your blog site and check that out. Because Atlanta Braves, right? Wasn't it Atlanta Braves was the baseball team? Because I do remember what you said about that. Because you said the fast runners are much faster, the best chess players are much better, and we're always talking about Brady and even among the best chess players and the fastest runners, there's also the GOAT being the greatest of all time. So and that's very different, because I guess what you're saying there, that doesn't follow a normal distribution. So, and the chess example I thought was very good. If you can dive into that a little more, which again, I'm taking abstracts from your book here.
Yeah, sure. And I agree. You have to watch the video in order to appreciate how much faster a fast runner is. And I will say that the guy who dresses up as the Freeze is a very good runner. He was a competitive runner when he was in college, but he's not even a professional. He is a member of the grounds crew who happens to have been a very good runner. So even when you see how fast he is, if you put him up against Usain Bolt, it would not be a competition by any stretch at all. And you would see exactly as you were just saying, that even among the elite runners, there's somebody who's even faster, and often by a substantial margin. And that's the case with chess as well. The top players by rating are substantially better. You could make a ladder where the best player in the world would consistently beat someone who was an elite grand champion. And then that elite grand champion would consistently beat someone who's one level below. And the hypothesis in the book is that this is the behavior that we get from log normal distributions, because they have that long tail. And it happens because of, I think, two processes. And one of them is a proportional gain process, where the more advanced you are, the more you're able to take advantage of resources and get even better. So there's this positive feedback loop where, in some sense, the rich get richer. Right. That's one of the causes. The other, and I was thinking about running speed in particular, might be something like a weakest link phenomenon, where in order to be an elite runner, in some sense, everything has to be right. You have to have the right muscles and cardiovascular conditioning, and there might be 5 or 10 or 20 factors that all contribute to your running speed. And if any of them are bad, you're probably not an elite class runner. So being out in the tail of the distribution means you have to get, factor A and B and C. And that logic operation, the and, behaves like multiplication. So it's like multiplying all of those factors together. If any of them are low, the product is low. And that, I think, can explain where these log normal distributions come from, because when you add up a bunch of random factors, you get Gaussian distributions. And when you multiply a bunch of random factors, you get log normal distributions.
And log normal are so good at showing when it's not linear anymore, and so you have those tails, and the fatter tails and the distributions are longer tails, as you said.
Yep.
No, again, and the book did such a good job of illustrating that. But looking back to the second chapter there, something I hadn't heard about before, which was the inspector paradox, which talked about these. Because a lot of times when we struggle with data and statistics, it's about these counterintuitive situations, right? And I think that was the deal with the when you're looking at a sample population where the particular object, it can be biased by the size of the object. Can you? And I know we're talking about it a little bit already, but can you delve into that inspector paradox, which
Sure.
I find fascinating?
Yeah, this one, I ended up having many examples of this over years that came up in the blog. And it was only when I started putting them together that I started to see these connections. But one of the examples, and I'll start with this because it's relevant to my time on a college campus, which is looking at the sizes of classes. Because the colleges will advertise, we have small classes. The average class size is, let's say, 35. But then when you get there, you start signing up for classes and you're in big lecture halls. You've got 100 people and you've got 300 people in a class. Something doesn't add up. And in fact, if you walk around campus and you survey a student and you ask them, how big are your classes? The average of all the responses might be 90.
Yeah.
At the same time, like the dean is telling you that the average class size is 35, and this looks suspicious. You think somebody's lying. In fact, those things can both be true at the same time. And what's going on is the sampling process, where when you ask the dean for the average class size, they're going to look at every single class on campus. So each class shows up in the sample one time. When you survey students, if a student is in a large class, let's say there are 100 of them, that means there are 100 students walking around that campus who will report that their class size is 100. And if someone's in a class with only 10 students, it means there are only 10 students walking around who will report size 10. So when you survey students, you are oversampling large classes. A large class is more likely to show up in your sample, and it's more likely by a factor that is the size of the class. If the size of the class is X, it will get oversampled by a factor of X. So both of those things are true at the same time. What's going on is that the meaning of the word average is hiding a subtle error, which is one of them is advertising across the population of classes.
Exactly.
The other one is averaging across the population of student experience. And they're both true. And they're both they're measuring different things. If you want to know what it's like to be on that campus as a student, the student experience is probably the right number to look at.
Exactly. And that's why I was saying earlier, it seemed like counterintuitive, but excellent example. And no, I find the book a fantastic read, and even your blog site, Alan, because when we always say, all models start with good data, that definition of data is always so hard to pin down. And we all know that data is biased in some respects, not, because in that same chapter where you discussed the inspector paradox, you were also talking about length bias sampling, which anecdotally makes complete sense. Like if you're looking at a data and the sample in that population, or your range of data you have is something to do with length or duration. When we ask, because I'd learned this before, and I think my earlier stats class, I think the example they were giving was TV shows and what's your favorite TV shows. It was like for a certain generation of people with friends, and sometimes it's the newest show or the latest movie, but a lot of times for TV shows, it's the ones that have been around the longest. So can you talk a little bit for our audience about the length bias sampling that you describe in your book?
Right. Yeah. So that's an example where rather than class size, you've got something that varies in time. And so when you observe the system, you're more likely to observe something that persists over a period of time. And so that ends up, there's kind of a combination there of length biased sampling, but also a kind of survivorship bias as well. You're more likely to observe things that have survived for a long period of time. There's one example of this is in looking at restaurants. If a restaurant is in a terrible location, the food is probably good. Because if it's in a terrible location and the food is bad, it probably won't survive any length of time. So the food's going to be good because it needs to be good.
That's a good example, actually. If I have to invest in a restaurant when no one ever advises, I think I'll start putting that as one of the criteria on there.
Yeah.
So another one, paradox you described in your book, which again relate to all these Bergson's paradox. I thought that was also pretty fascinating, where we incorrectly think two things are related because, again, looking at the data sample or the population. And I found out what I found interesting about that one, and I think, is that the one where you were describing your time as a volleyball player at MIT?
Right. Yeah.
Yeah, I think having known you for 9 years, coming to ODSC East, I always kind of knew you were a runner, but now I know you take part in the James Joyce Ramble, and then that you were also a student athlete at MIT when you were time there. But anyway, I digress. But please work that story in there, because I think our audience will find it fascinating as well. But yeah, Bergson's paradox.
This was, I think, maybe the first example of Bergson's paradox that I observed, although I didn't know the term at the time. If you go and you play competitive volleyball, you're going to see, first of all, a lot of people are tall. And if you see somebody out there who's short, the chances are that they jump really high. Either that or they might be the setter. But by and large, if you see somebody short, they can probably jump. And my first thought was that there might be something biomechanical going on there, which is that maybe short legs provide some kind of mechanical advantage that contributes to jumping ability. And if you remember, there was a player in the NBA named Spud Webb, who I think was only about 5'5", but he had a 40-inch vertical leap or something like that. He could dunk a basketball.
Wow, that's crazy.
And you think about, it turns out there is no biomechanical process happening here. Short people and tall people have the same jumping ability on average. What's going on is a selection process, which is, if you are short and you cannot jump, you probably don't play competitive volleyball. And if you're short, like Spud Webb, and you can't jump like Spud Webb, there is no chance that you're going to play in the NBA. So what we see because of the selection process is a correlation in the sample that doesn't exist in the world. Height and leaping ability are unrelated in the general population, but among volleyball players and basketball players, they are, I guess, anti-correlated, because the only way you get on the court is whether you're either tall or jump or both. And so it's the selection process that creates the correlation.
Gotcha. And for those who don't know Allen, he's quite tall. So I guess that's when you're thinking, like, I need to jump more. And I think that was that part of your chapter, which was a great title, which I'd love to expand on. Was it? It was. Let's look at my notes here. Causation, collision, and confusion. Which is a great title.
Right. And that comes about. So if you get into causal inference, one of the things that they use in order to explore these mechanisms is a causal diagram. And in particular, if you have two potential causes that cause the same effect. In the diagram, what that means is you'll have two arrows that come in toward the same box. And so they collide with each other. And so this phenomenon is also called collider bias. And so that's hence the causation and collision, collider bias. And then the confusion was an entire chapter that was based on epidemiological errors that were the result of collision bias or Bergson's paradox, whichever you prefer. One of the big ones is the low birth weight paradox.
Oh, yeah.
And this is an example, again, where there are two causes, which is, by and large, if a baby is born underweight, one of the potential causes is maternal smoking. If the mother was a smoker, the babies tend to be lighter, and so they're more likely to fall under this threshold of low birth weight. The other potential cause is, in some sense, everything else, all of the other causes of low birth weight, including birth defects. So if you look at low birth weight babies, their health outcomes tend to be less good, higher mortality, more disease. But if you select the lightweight babies where the mother was a smoker, the outcome is actually better than for a lightweight baby if the mother was not a smoker. And at first, that is paradoxical. It was called the low birth weight paradox. And the person who discovered it actually thought that maternal smoking was beneficial for low birth weight babies. His theory was it's harmful for normal babies. Maternal smoking is bad, but for low birth weight babies, it's good. And in retrospect, it seems absurd, and it is absurd because I've already kind of given away the explanation, which is that there are two causes. It's either smoking or it's something worse. Right. And so if you find out that it's smoking, that is in some sense good news, because that explains the low birth weight in a relatively benign way. Because it makes it less, it makes the other explanations like birth defects less likely.
Yeah. And again, as I mentioned previously, you have so many great examples woven throughout the book. But what I found extremely useful with all these anecdotes, stories, explanations, you also had a Python notebook for each chapter. It pretty much was for each chapter. So, and that's available on GitHub. So folks, you can go and try this yourself, whether you have the book or don't have the book, but we encourage you to get the book. If you don't have it, you can still play around these notebooks. And I found the notebooks really super useful to play around with this data and understand some of these paradoxes and work with the data. So I again, Alan, thank you for that. That's a great contribution to the open source community and those of us who are trying to dive deeper into this, and a great educational resource.
Yeah, can I just say, thanks for mentioning those. The book itself does not have any Python code in it and very little mathematics. I try to explain the ideas primarily using figures and graphs and, of course, text. But the notebooks, as you said, if you go, the landing page for the book is probablyoverthinking.it, Probably Overthinking It, and we'll provide the links. But from there, you can get, as you said, the Jupyter notebooks. They download the data, they execute the code, and they all run on Colab, so you don't have to install anything. And my hope is that that's a useful educational resource. Readers, if you want to dive deeper, it's available. And if you're teaching a statistics class, I hope this can be a useful resource for people.
No, absolutely, 100% is. So you can, very, very useful. Another topic, and again, I love how you come up with these titles. I don't know who you work with to come up with these titles, but the distribution of disaster. I gotta use that phrase. And then distribution of disaster and black swan events was also something I really loved because, of course, when you think about black swan events, not sure if our listeners know about this, but there was a famous, the very famous Nassim Nicholas Taleb. He introduced the black swan concept. I think he introduced the concept of black swan event. Mm-hmm. I think it was around this concept that until the 17th century, everyone assumed that swans were white. And then with Cook's Voyage to Australia, I guess they found some black swans. But I do remember that book because I bought that book in 2007. I was working for a hedge fund in London, and I was trying to do option trading based on this because trying to figure out 2 sigma movements. And then I was still trying to figure it out when the financial crash happened. So I was like pretty much a good few weeks or months. I like to think I was a few weeks late into implementing because I was working in a hedge fund. In a hedge fund, you always try and play market up movements. We can make a lot of money when markets go down. So they say the 2008 financial crisis was a major black swan event, but basically it's unpredictable or extremely rare events. But so I'm pretty familiar with the black swan event, and some people was, but the distribution disaster is great though. Can you elaborate on that?
Sure. Yeah. Okay. So we talked about Gaussian distributions,
right?
And we talked about log normal, and the feature of the log normal is that tail that extends off to the right. What the chapter about disaster talks about is actually an even longer tailed distribution. It's the student t distribution. And compared to even a log normal, that tail extends much farther out to the right. And if you're talking about bad things, that extreme right tail means that you have very rare catastrophic events. And so there are two things to think about. And one is how often do they happen and how big will they be? It turns out a lot of phenomena in the natural world follow these very long-tailed distributions. If you look at things like the energy released in an earthquake, the sizes of the craters on the moon, asteroids in the asteroid belt, all have this phenomenon where most things are very small, and then occasionally you get this extreme, as you say, black swan event. So this happens in natural systems, and it also happens in the stock market. If you're trying to predict, extreme events, especially extreme negative events, you can look at the past history, and you can look at like daily changes in the Dow Jones Industrial Average for the last 100 and some odd years. And you can look at how big the change is every day. And now the question is, how do you make a prediction? So there are, I think, two versions of the black swan hypothesis. And I think the weak version says, if you use a Gaussian distribution to describe this data and you try to predict what the tail is going to look like, your predictions will be hopelessly wrong. In fact, what you just described about a 2 sigma event, when you're talking about sigmas, if you mean the standard deviation of a normal Gaussian distribution, as soon as you say the word sigma, you're in trouble because it implies that you're using the wrong model. If you mention kappa, you're probably in good company because that's the tail parameter of a student t distribution, or alpha if you're working with Pareto distributions. There are several different of these long-tailed models. So the weak version of a black swan says basically, if you use a bad model, your predictions will be bad. That's not surprising. The really hard version of this is predicting things that we have never seen. And stock market is one. We've seen some big drops in the stock market, but there's no way to know whether we've seen the biggest. The other example that I use in the book is solar flares, which is a potential hazard to life on Earth in the extreme values. And we've seen about 100 years of reliable measurements. And so we know the biggest one that we've seen so far. But we have seen solar flares on other stars that are 10,000 times bigger than the biggest one that we've seen. And with 100 years of data, there's just no way to make a meaningful probabilistic prediction about whether that can happen and what the probability is. So that's the hard version of black swans, is when we really just can't generate a probability at all.
Yeah, that's fascinating because I guess, would you say by any measure, I guess COVID was a black swan event because the last outbreak of something similar was, 1914 or 1918 to 21. And that's a fact because I know you have some COVID examples in your book. And I was, because, I have family in the UK and Ireland, I was really following what they were doing in the UK because they had various statisticians and they just handled it differently, and they were very focused on the data and very focused on the models. What were the surprises that came out of the pandemic, I guess, in terms of statistics? Because I know you had some good stories in your book. I don't recall them quite now, but obviously didn't get it right all the time. But are there any good lessons that statisticians and data experts are taking from the pandemic and how we measure data and whatnot?
Yeah, well, certainly one of them, you mentioned the UK. I think they, among countries dealing with the pandemic, did some of the best work collecting data, analyzing it, and making it available. They made almost all of the data publicly available immediately, which had an amplifying effect because other countries followed. that allowed you to make comparisons across countries, see what's working, see what's not. So I think that was a really exemplary way to go about it. Was the pandemic a black swan event? It was more predictable than we might like to say, and inevitable that there will be more. So we need to be prepared. We're not. I don't think we've learned our lesson by any stretch. And part of it is, again, looking at the way statistical arguments were made. If everybody became an armchair epidemiologist,
right.
and including people on podcasts spouting statistics, and sometimes
not this person, not this person.
Right.
Just want to put a disclaimer out there. I wasn't one of those people. We started the podcast just a year ago, FYI. Look, sorry, go ahead. I didn't mention that.
No, I say this as someone who spouts statistics on podcasts. But there was a notorious example of a journalist who was on the Joe Rogan podcast, who talked about a particular period in the UK when, if you looked at people who were dying of COVID, 70% of them had been vaccinated. And the guest, the journalist, said that, and the podcast host was astonished. 70%, how can that be true? Well, the answer was that in that age group at that time, 90 or maybe 95% of those people had been vaccinated. So if 95% have been vaccinated, and among the people who die, 70% are vaccinated, what that means is that the vaccinated people are underrepresented in the mortality cases, which is exactly what you would expect if the vaccine is safe and effective, which, by the way, it is. So it turned out that same number, that 70%, it sounds like the vaccine doesn't work, but in fact, combined with the 95, you can now work backwards and figure out how effective the vaccine was. And in that age group, it was, I don't remember the number, but it might have been 70% effective at preventing death. I mean, maybe 80%, which is highly effective.
Right. And that would be an example of Bergson's paradox, right? Which we were talking about earlier.
It is. I think we can. I used it, and some of these things overlap.
Yeah.
But this was also an example of a base rate fallacy, where in this case, the base rate of vaccination is 95. The observed event rate that you see is that 70% of the mortality cases had been vaccinated. And what you can back out from that is the efficacy of the vaccine. The other calculation that I did was to figure out that during that month that the journalist had kind of cherry-picked that piece of data, there were about 4,000 deaths that were prevented in the UK. So just in one country, just in 1 month, 4,000 prevented deaths because of those vaccines, which is pretty good.
Yeah, that's excellent. That's 4,000 very happy families. Trust me, everyone counts. Yeah, and Alan, just as we wrap this up, one thing that inspired us and the team to start ODSC was there's an infinite availability of learning material out there, but I always found it fascinating that small nuggets of information can really change my perception on a task or something I'm working on. And shifting a bit away from the statistics part of it, but you were at ODSC East last year. I think we had the conference in May, and I remember you had one slide on it, and all it said was biased, because people take phrases in terms, like you hear lectures like there's always this bias in the data, these traps in the data. And even myself, up until that point, I was saying, oh, the data is biased. What I meant by that, it was like, generally the data is good, but there's always some kind of bias in the data because, you don't have the universal population size or sample size, data set. But what struck me is when you said bias does not mean off by a bit. it's a polite way of saying it's completely wrong. And I found myself repeating that to my team and like, are you doing all the analytics and I observe this data the way you need to? I thought that was a really astute observation. Because those of us in the data space, I think, to say, yeah, it's off by a bit, and you're saying, no, it's wrong. Yeah, I don't know if you want to elaborate on that, or that's just a statement of fact. I don't know. I just want to credit you for that.
Well, thank you. That one, it comes up in part because when you take an intro stats class, the place where you first hear about bias is often when you estimate the standard deviation and you learn about the difference between taking the standard deviation when you divide by n or when you divide by n minus 1, because one of those is a biased estimator and the other one is an unbiased estimator. And so, for any medium to large value of n, it's a very small difference. It doesn't really matter. And so if you leave that class, exactly as you said, if you think, well, bias just means I'm off by a little bit.
Right.
No, these sampling biases, where what's happening in your sample is very different from what's happening in the world, you can make it 180 degrees wrong, where you see a positive correlation in the data, but there's actually a negative correlation in the world. That's not off by a little bit. That is, as you so eloquently put it, wrong.
Yeah, no. That was a great insight. And you're giving another talk at ODSC East in April, one of those days in April, 23rd, 24th, 25th. Can you tell us a little bit about, I'm not sure how much you've thought about it, but give us a little insights of what's the topic you're going to be discussing.
Sure. Yeah, I'm looking forward to it. This one is about survival analysis, which I think is the most underrated area of statistics. It tends to be an advanced topic, and so a lot of people don't see it, but it's, I think, a very powerful set of tools. And so I'm going to talk about some counterintuitive behavior, and I'll explain. If you start with something like light bulbs wear out over time. And so if you have the choice between a new light bulb or a used light bulb, the new light bulb is probably better. It will probably last longer. That's what we expect. Things wear out, right? Turns out there are other examples where the longer something has been going, the more information you have about it, and that implies that it is likely to keep going. One of these examples is very often after a cancer diagnosis. The prognosis gets better and better over time. So at the time of diagnosis, the median survival time might be a year, let's say.
Just by surviving, yeah.
But if you do survive a year, then now your median remaining survival time might be a year and a half or 2 years. And it will keep going up the longer you survive after diagnosis. What that implies often is that the condition was found early and that the treatment has been effective. So survival implies information, and the information implies longevity. So you get the flipped behavior where used, in this sense, having survived for a while, is better than new.
Excellent.
So yeah, look, I have a few other real world examples that I'll talk about, and I'm looking forward to it.
No, excellent. And so the best place to follow you is on your blog site?
Yes, Probably Overthinking It. I post about once a week on average, and yeah, that's a good place to go look.
And then you mentioned a podcast as well. How often are you doing the podcast? Because I need to start subscribing to those.
Right, I'm not doing my own. I've appeared on a few
podcasts
where I study statistics.
If you're doing your own, I want to listen in those. So, Allen, thank you so much. This has been a fantastic conversation. Again, so many great insights. Really enjoyed the conversation. Very much looking forward to your talk at ODSC East. I'm doing a little work with a venture capital firm, and we were just talking the other day about survival bias for startups and that exact phenomenon you're just talking about and the problem with that. So I'm going to be maybe dragging a few of those along to that talk and listening myself with rapt attention. But again, I would encourage everyone to check out Alan's website. You have a link to all your free books there, and also a link to your book, which is available in Green 3 Press. And I believe, are we doing a book signing at ODSC?
I think so. I'm not sure yet, but
I'm not sure either.
But I'll be there and looking forward to talking with you.
Remember, the first one we did, like, we didn't know what a book signing was, and we got 20 of Alan's books. There was 400 people in line. It was like the longest thing I've ever seen. And I think by the end of it, people couldn't see around the corner. They were just joining the line because I don't know what's on this. I don't know what this line is for, but I'm sure it's for something good, and they weren't wrong. Alan,
great.
Truly appreciate your thoughts and insights and your valuable time. Thank you so much. So on behalf of myself, the community, and we'll see you in a few short months.
Thank you very much.
Bye for now.